Okay, so one thing I saw online recently is very interesting. Like I was subscribed to the American Statistical Association mail list, and I saw that there's a recent discussion about how to teach the two sample t-test, which is related to what we did here because we said we could, in our last lecture, we said we could use t-test for testing whether one coefficient in a linear model is zero or not. And here we are talking about t-test in the context of linear model, but you know the more general t-test is just to compare two samples, right? You want to see whether the two samples come from populations with the same mean. And I don't know what you guys learned in your previous education, but in my course, I always tell students, okay, for t-test, if your sample size is not too big for the two samples, then you cannot apply the central limit theorem. Then you must check whether you can safely assume your two samples can be approximated by a normal distribution, or they look like normal. That's what we taught. But then, very interesting, from that discussion, I saw that there are voices, and actually a 1987 paper about the robustness of two sample t-tests. So basically, there are voices supporting using t-test for data that are even binary or counts, discrete counts, which are clearly not from a normal distribution. So then it seems that the issue from the discussion is that people think, okay, you should be cautious using t-test if your data are clearly skewed. Like if you have clear outliers in your two samples. And I didn't check that 1987 paper myself yet, but I can actually post that information to our YouTube video, then you can check it out later. But I just want to say that it's so tricky sometimes when we talk about the test assumptions. In practice, even though those assumptions are violated, but your test will still be robust. I think this is just one example of that. And so in the class, we teach you the cleanest version, like what assumptions are used to derive the test statistics, null distribution, etc. But in practice, people may tell you something different. I'm just using this as an example for you to be aware that, okay, statistical analysis in practice is sometimes a lot more trickier than what we cover in the class. Okay, so that's the beginning, a story I just read about. And let's just give you a quick recap of what we did. So we talked about the linear model, multiple linear model, the matrix form, and the point estimate, the OLS estimate, this formula, which is the key. And then we derive its variance or covariance matrix in this form. And then we start to talk about how to do inference about beta. And the inference, we give you three tests already. The first one is for a single beta j. For a single beta j, we talk about t-test. You can test whether this beta j is zero or not. And you may also want to test multiple elements in beta together. And for this one, we give you the Wald test, which allows you to test whether these P2 elements are zero. And this is based on this Wald statistic, okay? It will convert this P2 dimensional vector you estimate into a scalar. And this Wald test is equivalent to t-test if P2 is only equal to 1. And finally, we give you the likelihood ratio test, which can play a similar role as the Wald test for multiple linear model. So here, in the likelihood ratio test, you consider two nested models. So under the H0 or null hypothesis, you would have a smaller model by assuming certain coefficients are equal to 0, which means that you just do not consider those predictors in your model. That's the smaller model. While the alternative is the full model, which includes all the P-1 predictors. And then the likelihood ratio test statistic is constructed by the difference of two log likelihoods. So one is by using the beta hat or beta, given that you maximize the log likelihood under the null hypothesis. So in other words, you are doing maximum likelihood estimation by constraining beta 2 to 0. That means that you just exclude those predictors from your model, use the remaining predictors, do the MLE. And in the multiple linear model case, the MLE is equivalent to ordinary least squares. And this is by doing the MLE or OLS using all the p-1 predictors. Then you have log likelihoods for both models, and then you do this log likelihood difference. And here in the linear model with normality case, this is just equivalent to the residual sum squares under the null hypothesis versus minus the residual sum squares under the full model. And you know that here the first RLS must be greater or equal than the second. Since the more predictors you include, the smaller the RLS. This is what we would expect by model fitting. And here the last issue is about how do we plug in for the sigma square, which is an unknown parameter. So here we use this estimator, which corresponds to the MLE. So this term is actually the MLE of sigma square under full model. We plug this in, and then we can get this estimator for the -2 log likelihood ratio. And we know that asymptotically, as when our n is large, that's the number of observations for fitting a linear model, we would actually have this test statistic approximately following chi-square distribution with p2 degrees of freedom under the null hypothesis. So I spent quite some time to talk about likelihood ratio test because it's very general, and you can use it for our other models, including the generalized linear model, which we'll cover next. Okay, so I think I had a take-home question for you guys in our last lecture. That is, if I have two possible options. One is to test. So if my question is, let me put it here. So if my question is this null hypothesis, that is the p-dimensional beta vector is 0, then I have two options. One is that I test each beta j equal to 0. So let's say I would have hj1, which is beta 1 equals to 0, to h0p, which is beta p equal to 0. I could do p tests simultaneously. And my option 2 would be just do a Wald test or likelihood ratio test. Then what are the benefits of each one? And which one should I choose?
What would be the likelihood ratio test under the null of all betas equals 0?
Okay, so that's a very good question. So if you have this likelihood ratio test, okay, maybe I should make it more clear. Probably I should just constrain myself to the predictors. I think that's a good point. So if I call this beta 0, and let me call this beta, I'll give this a beta prime. Okay, so this beta prime is just p-1 dimensional. So here I'm only testing beta prime equal to 0, which means that I exclude the intercept. So then in this case, so beta prime, I'll just write it down as beta 1 to beta p-1. Okay, transpose. Then this beta p-1, then I have p-1 tests. Okay, then I can consider either doing p-1 test or a Wald test. So in this case, if you're doing a likelihood ratio test, your smaller model will just be the intercept-only model. That means if you fit that model, you will use the average of your y1 to yn as the fitted value for each yi.
Can't they be jointly significant but individually insignificant?
Can it be jointly significant but not individually significant? Is that what you said?
Yeah, I mean, I think that'd be
Yeah.
a reason to use the Wald test or likelihood ratio test.
Exactly. So it could, that's very likely. Yeah, so it's jointly significant means what? It means that using this linear model, you are doing a better job or fit your data better than just an intercept model, right? But it's possible that not a single one of the coefficient is significant. That means, okay, probably each effect is very small. And given your data, you do not have significant evidence to reject the null hypothesis. But here is the thing. So not rejecting the null does not mean, okay, we believe beta 1 is 0. It means the decision is inconclusive. We cannot say, or indecisive. We cannot say anything, but it doesn't mean we accept the null to be 0. So that's a very important aspect to think about when you interpret the hypothesis testing result. So yeah, as Nathan said, very good point. So it's possible that you reject this H naught beta prime equals to 0, P minus 1. Okay, but not these individual tests. Okay, and one more thing is that if you do this multiple tests, it's very important to bear in mind that you need multiple testing correction, right? And here we didn't touch that aspect yet. So that's another hassle if you want to go through this multiple testing route. And after doing the correction, you will be more conservative and you are less likely to reject any of those P minus 1 tests. Okay. So that's a side note and a left out question from last lecture. Today, we're going to continue our discussion about ANOVA. So this ANOVA is a very widely used analysis in practice, and it stands for Analysis of Variance. So how do we use ANOVA for? So basically, you can consider ANOVA as the decomposition of variance in our y's, y1 to ym, the sample level variance. So let's say that if you recall our notations, we have our y, that's a vector, right? And instead of having the vector form, we can also write out y hat. So y hat is just the predictive value. We can start from the vector form and then go to individual ones. So if you recall, if we use the OLS estimate, it's x times beta hat. If you plug in the beta hat formula, it's x transpose x inverse x transpose y. And if you recall, we actually give this a notation H, the hat matrix. Okay, so in other words, you can see that there's an interesting relationship between y hat and y. That is, given y and given you consider the design matrix to be fixed, so you can just do a linear projection of y by left multiplying h, then you get y hat. And what does this imply? One thing is this. Let's imagine, what if I left multiply x transpose on the left-hand side and right-hand side? So you can see that if I do x transpose y hat, I'll see something very interesting. So here, I can just left multiply x transpose. Okay, the interesting happens, that is, I will cancel out x transpose x here. So in other words, I will have this nice equation that is x transpose y equals x transpose y hat. So regardless of using y or y hat, if you do x transpose, you get the same thing. And this is what? This is p-dimensional. You get the same p-dimensional, 2 p-dimensional vectors. And if you remember, the first column of x is 1, right? It's all ones. That's the intercept. Then the first row of x transpose is all ones. So that will give me 1 transpose times y hat, and this one is n-dimensional one, is equal to 1 transpose y, okay? Because 1n is the first row of X transpose. And then this tell me what? This will tell me summation of yi hat, I from 1 to n, is equal to summation of yi, I from 1 to n. So this is a very important result about linear model. That is the sum or equivalently the average of your fitted responses is equal to the sum or average of the original responses. Okay, and this is a central result we're going to use in ANOVA. Because of this, because they share the same mean, we can actually write out, okay, I'll write down the important formula for ANOVA. That is, if we take the summation I from 1 to n, yi, we subtract the mean, y bar squared. We can decompose it into 2 terms. One is I from 1 to n, yi minus yi hat squared plus summation I from 1 to n, yi hat minus y bar squared. Okay, you can verify this result yourself by just doing, say, you do a subtraction of yi hat, and then you add it back, add a yi hat back, and then you open that quadratic term and do cancellation. You can verify this, and you will need to use this result. That is the yi hat and yi share the same average as y bar. Okay, so this y bar is equal to the average of yi as well as the average of yi hat. And we give these terms names, okay? So the first one, the total one, we actually call it sum of square total. The T stands for total. And this one, we call it SSE, sum of square error. And this one is sum of square regression, SSR. So SST equals SSE plus SSR. This is the foundation of doing ANOVA. And if you recall, we said that this SSE also has a name RSS. That's what we used last time. So RSS is residual sum squares. It's just 2 terms for the same thing. Okay, so then in the ANOVA, we're going to give you this decomposition. And for each term, we're going to give you its degree of freedom. And then it will allow us to do F-test just based on these terms. So you can consider ANOVA as a traditional, classic, or convenient way of doing statistical test for the whole model. Whether this model, as I said, whether this regression model is doing anything better than an intercept-only model. That's the question to be answered by ANOVA. So then you see ANOVA can be considered as an alternative to your Wald test, to the likelihood ratio test, but they're essentially about the same thing. Okay, so let's see. So ANOVA, people write it in the table. Okay, so let's say that you consider the baseline model, or you can think of as the null model as just the intercept-only model, okay? So in that case, if we write it down in terms of our linear model form, you would just have yi equals beta 0 plus epsilon I. And here, the epsilon i's are still IID, normal, zero mean, common variance, sigma squared. So we do not include any predictors. That's our baseline or null model. And it's intercept only. So we can just use this one for now. That's the That's the thing ANOVA is comparing against. That just as a side note, we're going to talk about this later when we talk about whether the model are overfitting or whether the model is just doing too much fitting. So here versus the other extreme, I'll put it here, but we're not going to use it for now. The other extreme is what we call saturated model. So in the saturated model, you are just assuming every response has its own mean. So we can write it as yi equals mu I plus epsilon I. So here the parameter, then you can say that we have n parameters. So we have mu1 to mu n. Each one is a parameter. And you see that this model becomes, you have n observations, each one has its own parameter. So it's not like the linear model, we are trying to reduce the number of parameters to p, right? We're going to use predictors to reduce the number of parameters. But here we don't use any predictors to link those responses. We just assume each one has its own mean. So it becomes one parameter, one observation scenario. Then what would be your MLE? You can naturally think, okay, if you still have this assumption, epsilon I, then clearly you can say, okay, the MLEs, mu I hat, in this case, is just your yi. Basically, you're not doing any change to your data. Your fitted value would just be your observed value. So it seems to be meaningless, but it serves as the other extreme for us to evaluate our linear model. Okay, so now let's look at ANOVA. So the ANOVA table is to compare a linear model to the null model, to the intercept-only model. So what we do is to, okay, let me put it here, compare a linear model versus the null model. Okay, so in the ANOVA, we have those columns. The first one is what we call source of variation. You can consider this as a description. And the second one is sum of squares. We call this SS. And the next one is degree of freedom. We write this as DF. And the next one is mean squares. So the mean squares is basically SS divided by DF. And finally is the F statistic. It's a ratio, okay? F ratio. Okay, so let's look at each one. So for the source of information, as we shown here, we divide the source of we have the sum of squares for total, error, and regression. So we'll have them here. So the first one we put here is the regression. And this one is what we call SSR. Okay. And the next one is the residual. We have some of the remaining variation in the residual. We call this SSE. And putting them together as a total, we call this SST. Okay, we have these already. And then the key thing comes, the degree of freedom. What's the degree of freedom? Let's look at this one first, SST. This is the most obvious one. Here we have n observations, and we tie them together by subtracting the mean, right? So by subtracting the mean, we basically shift them to center 0. And this is like we lose 1 degree of freedom, okay? So here the degree of freedom becomes n-1 because of the mean subtraction. So similarly, let's look at here. SSR, it's about y1 hat to yn hat minus y bar. So then it will be related to the degrees of freedom in my y1 hat to yn hat. Okay, now it's here. So if you recall, in our regression model, basically, this is something we had shown you before. It's regarding this H. Okay, let me put it here. So this is what we did for the property of the hat matrix. The hat matrix has trace P. So we said this, and we said, okay, given that here we have this y hat equals H multiplied by y. So you can essentially think, okay, now the degrees of freedom in y hat is P as opposed to N. So let's say that we can consider this y to be a point in an n-dimensional space. Then after this transformation, you can essentially embed your y hat in a p-dimensional space. That means using p dimensions only, you can describe those n coordinates in your y hat. So that's why y1 to yn is p-dimensional, and you have p degrees of freedom. Sorry, y1 hat to yn hat has p degrees of freedom. And you subtract the mean, which means you lose 1 degree of freedom. So then this becomes p minus 1. Then the nice thing about the degrees of freedom is that they're additive. So these 2 degrees of freedom add up to this one. So then you can clearly see the residual degree of freedom is n minus p. Even though I don't know this rule, I can still derive this n minus p just from the origin, because here the residual is what's left after you fit the linear model, right? So which means that the linear model itself accounts for p degrees of freedom in my whole model. And so then, you know, the linear model itself includes the intercept as well. So intercept is 1 degree of freedom, p minus 1 predictors are p minus 1 degree of freedom. So then together, the model has p degrees of freedom, but your data has n degrees of freedom. So the what's left in the residual is n minus p. So hopefully this makes sense to you. And then in the ANOVA table, your next is to define the MS. So correspondingly, you have MSR, MSE, and MST. So it's easy. You just do MSR equals to SSR over P minus 1. And MSE is equal to SSE over M minus P. Okay, finally, the F ratio. That is our F statistic. And here you can just define it as MSR over MSE. Okay, and this F statistic under the null hypothesis, which is that, okay, if you are under the null model, then this F statistic will follow an F distribution with 2 degrees of freedom, P minus 1 and M minus P. That's it. And you can see that it shares some similarity with the Wald test. In the Wald test, we also have the F statistic. But over there, we actually define it in a slightly different way. So the Wald statistic and the F statistic here are not the same thing. But very interestingly, they are asymptotic distribution, this null distribution, or if we're under the Gaussian normality model, it's not asymptotic, it's exact. This null distribution is the same. So it's basically the numerator degree of freedom is the number of additional parameters in your model compared with the null model. So you have P minus 1 additional parameters. Over here, if you check the Wald test, you see we have the P2, and N minus P. Here, P2 is also the number of additional parameters in your model. And N minus P is the degree of freedom in your residual. So the same. Okay, and how can we show that this is exactly F distribution given we are under the normality assumption? So still, it will be based on the definition of F distribution. That is, you have the numerator as a chi-square random variable divided by its degree of freedom. So here, SSR is a chi-square random variable divided by P minus 1. That's the numerator. For the denominator, it's another chi-square, SSE, divided by its degree of freedom. So that gives you denominator. So that's why it's a F distribution. Okay, that's the ANOVA. So it's about testing the whole linear model, whether it's fitting better to your data compared to the intercept-only model. Now we're going to introduce another useful one. It's actually a little trickier, and it can be very easily mistaken in practice. It's called hierarchical ANOVA. Okay, so in hierarchical ANOVA, what you do is that you are trying to input your random variable in your model in a sequential order. So it's comparing these two things. So it compares, okay, let's say that we have yi equals beta 0 plus beta 1 x1I plus beta 2 x2I plus epsilon I. I have two predictors versus yi equals beta 0 plus beta 1 x1I plus epsilon I. So I'm comparing the model with a smaller model by excluding the last predictor to be included in the model. So essentially, this hierarchical ANOVA is to test the conditional contribution of the x2 predictor given that x1 is there. Okay, it's nested model. And then you can see it is equivalent to what? First, in this case, it is equivalent to t-test because you're basically testing whether this beta 2 is equal to 0. Second, you can also think of it as a special case of the likelihood ratio test where you have two nested models. Okay, so speaking of that, before I go into the hierarchical ANOVA, I want you to ask a question for those of you who have learned linear model before. So in this model with two predictors, how should I interpret beta 2? So what does beta 2 represent? We often call it the effect size of the second predictor, right? So beta 2. So we have this term, effect size of x2. But don't forget that this is all conditional on that x1 stays the same. Conditional that x1 stays the same. So in other words, this effect size is a conditional effect size. It's not a marginal effect size. So what I mean is that if I write, so versus if I write this model as yi equals beta 0, let me call this beta 0 prime plus beta 2 prime x2 plus epsilon I. So in this model, so here I use the same notation, but I just want you to be aware that they're not actually the same thing because here, when I exclude x2I from my model, this beta 1 do not mean the same thing as the beta 1 here. So probably I should also do this. So in this case, I want you to be aware that beta 2 is not equal to beta 2 prime. They do not mean the same thing. So without x1 in the model, the effect size would be changed. But in statistical inference, okay, when we write down a model, we often assume like only one of them is what we call a true model. So that's why you would not simultaneously assume both. You will start by assuming this one, this is a true model. And then you want to go ahead and test whether beta 2 is 0. Because if it is, then it doesn't make sense to include x2 in your model, right? So that's it. So I want to say that here, beta 2 prime is just a marginal effect size of x2 by having it as the only predictor in the model. And one more thing I want to ask you as a question is that, okay, let's say I'm doing ordinary least squares. So in doing ordinary least squares, so does my beta hat, the p-dimensional OLS estimate change with the ordering of columns in my design matrix? This is a question for you. Does it change or not? Of course, the order in the elements in the order in the beta hat will change. But if I just restore the order, will it be the same? If I put x1 in the first column versus I put x2 in the first column versus I put the intercept to the last column.
No.
Actually, no, it will stay the same, right? So it's only a permutation, but still the values will stay the same. Okay, no, only permutation. Yeah, this is a thing to keep in mind. It's a very important property in the linear model. That means you do not need to care about the order in your model, about the predictors in your model. And just as a related content, you may want to check out the recent work, which is regarding the interpretation of black box prediction algorithms like random forest, like gradient, like the like the XGBoost, those kind of things. So you can check out this. So there's something called SHAP. So it's an interpretation measure, and it borrows the idea from linear model. So what it tries to do is that no matter how your orders are, the ordering is for the predictors, they will give you the same importance measure for each predictor in a black box model. Okay. So let's come back to our linear model. So having said those about the interpretation of beta 2, let's look at what the hierarchical ANOVA does. So in hierarchical ANOVA, the order does matter. Okay, so here when we say it compares those two models, it means that we consider x1 to go first and x2 next. Okay, so let's look at the table. Source of variation, SS, DF, MS, and F. Okay, so in this hierarchical ANOVA, the first source of variation is the first predictor, x1. Okay, and we will have SSR. SSR1. How do we define it? So it's basically the regression or the fitted value using the x1 as the only predictor here. So in other words, this is defined as, okay, let me put it here, sum I from 1 to m. And here the fitted value is beta 0 hat plus beta 1 hat x1i. And this is your fitted value minus y bar squared. That's SSR1. So you're only using the fitted value by including x1 only. But just to be sure that you understand this beta 1 hat is still from, so these two things are still from the OLS of beta 0, beta 1, beta 2 together. So still in this hierarchical ANOVA, you only fit the bigger model for once. And then you take the OLS coefficient for intercept and for the coefficient 1 as beta 0 hat and beta 1 hat. And you construct the fitted value as it is, and then you do the sum of square over the mean. That's the first term. And I'll tell you that you will not need to care the first row so much in the hierarchical ANOVA. So let's continue. x2 given x1. Okay, that's the second source of variation. So here, SS for this x2 given x1 is defined as the SSR12 by having both terms in your model minus SSR1. So here, SSR12, probably I can use another sheet of paper. So SSR12 is just as SSR in the simple ANOVA. That is, you use the fitted value from the whole model. here we would have beta 0 hat plus beta 1 hat plus beta x1i plus beta 2 hat x2i minus y bar squared. This is SSR12. And we know that this one should be bigger or equal than SSR1. The reason is that we know more variations captured in the fitted value using both predictors. Okay, and one more thing to say is that if there's an interesting relationship, that is if we define SSE12, okay, that is what? That is, I just take the difference, square difference between the original response and the fitted response. Okay, x1i plus beta 2 hat x2i. And correspondingly, I could have the sum of squared error given predictor 1 only. Okay, so if I do that, then there's an interesting relationship. That is SSR12 plus SSE12 equals SSR1 plus SSE1, right? Because the sum of both is equal to SST. So I would have this. Then I can have an interesting relationship because SSR12 is bigger than SSR1 and SSE1 is bigger than SSE12. I can show that I have their difference equal. So I will have this relationship. Okay, so coming back to the hierarchical ANOVA, right here, this is the additional contribution of predictor 2. And finally, we have the residual. Residual is clearly SSE12. By having 2 predictors, what's the remaining residual? And then total, SST. Now I need to deal with the degrees of freedom. It's clearly n-1 here. And for x1, since I'm only introducing 1 predictor, clearly its degree of freedom is 1. Okay, and over here, I add another predictor, its degree of freedom is 1. So please note that here, if you compare to the simple ANOVA, I have p minus 1. The reason I said is because of the existence of intercept. So in addition to the null model intercept model, I introduced p minus 1 additional predictors. So that's why I have degrees of freedom as p minus 1. And here, I first introduce 1 predictor, that's 1 degree of freedom. Then I introduce another predictor, that's 1 degree of freedom. So now with 2 predictors and an intercept in my model, so the model has 3 parameters: intercept, coefficient 1, coefficient 2. And then the residual's degree of freedom is n minus the model complexity. So that's n minus 3. Okay, then I can have correspondingly MSR1, MSR2 given 1. Okay, and this is, so I can define this as, SSR2 given 1. Okay, that's the additional contribution of predictor 2. And I have MSE12. So those can all be calculated coordinate. Okay, one interesting thing here is, so in R, if you do this hierarchical ANOVA, I'm going to give you the command shortly. So if you do this hierarchical ANOVA, R will give you an F statistic here and an F statistic here. But I want to tell you that it doesn't make sense to me to talk about the F statistic here. I don't know how to interpret it. And this was an issue we spotted the first time I taught this class. So I would still say that for now, let's think this one is not so meaningful unless you figure out what it says. You can let me know. I think the only meaningful quantity is here. It's the F, that is MSR2 given 1 divided by MSE 1, 2. Okay, and the null distribution for this F is, okay, F distribution, the degree of freedom is 1 and n minus 3. So it's the degree of freedom of this and this. And so here, what's the null hypothesis? The null hypothesis is beta 2 is equal to 0. That's what you're testing. So in other words, my take-home message for you is that the hierarchical ANOVA is only meaningful for testing the last predictor you have in your model, whether the last predictor has additional contribution or not. But for the first few predictors, here I'm just having one predictor for simplicity. I don't think the F statistic makes sense. The reason is that when you calculate this SSR1, your beta 1 hat is from fitting the full model. It's not from fitting the X1 only model. So that's why you cannot interpret this F to mean whether X1 as itself in the model is meaningful or not. It's not. So just use this as the only test that you can take out of the hierarchical ANOVA. So which means that does the X2 has additional contribution given all the existing predictors in the model. Okay, so now finally I want to say that in R, you can get a hierarchical ANOVA by doing this summary, and you use the linear model function. If you do this y tilde x1 plus x2. This is the R command for doing linear model. Then you will give you the hierarchical ANOVA table I gave you here. So the interesting thing is that you need to care about the order. So in R, if you do this, it will not be the same as if you do still summary, but you put x2 before x1. If you do that, then you will get two different hierarchical ANOVA. Because for the latter, okay, for the latter, your hierarchical ANOVA will be x2 first, and then x1 given x2. And the F statistic is about the additional contribution of x1. So it's not the same. But interestingly, even though the hierarchical ANOVA is different, but overall, the y hat will be the same, right? Regardless using x1 first or x2 first, you will get the same y hat, and the beta hat will also be the same, just subject to permutation. Okay, so that's the linear model part, ANOVA, hierarchical ANOVA. Now, some interesting take-out message from the model is the coefficient of determination. This is also a very important criteria we get out of the linear model, coefficient of determination. We call this R squared. And this R squared, it can be defined just based on the three terms, SSE, SSR, SST. So it's defined as this. Okay, if you take the yi hat minus y bar over yi minus y bar squared. So you can clearly see it's SSR over SST. So that's how much of the total variation I see in my data can be explained by the regression model. So the larger the R squared, the better the model fits, right? In the ideal case, the R squared can be 1. That means when your yi hat all equal to yi, you will have the SST equal to SSR. So R squared then becomes 1. And then based on the relationship between SST and SSR, I can write this. Then that will give me 1 minus SSE over SST. And a very interesting coincidence in the linear regression is that when you only have one predictor, okay, so with simple linear model, let's say that you have yi equals to beta 0 plus beta 1 xi plus epsilon I. Only have one predictor. Then very interestingly, this r squared, just by coincidence, is equal to the square of the sample correlation, Pearson correlation, between y1 to yn and x1 to xn. It's just equal to this r squared, where this r is the Pearson sample Pearson correlation between these two vectors, y1 to yn and x1 to xn. So the observations of xi. So that's a very interesting coincidence. And you know that the sample Pearson correlation is symmetric between those two vectors. However, it seems that the r squared is not symmetric, right? Whether you take yi as the response is different from what you take xi as the response. But surprisingly, the r squared is symmetric. So although we know that these two models, I put it here, is not equivalent to, if I say xi equals to, let me put as gamma 0 plus gamma 1 yi plus, let me call ei. Even though these two models are not the same. And just as a side note, you can check that if you do all of S for each one, they are not reciprocal of each other. Okay, so if you can check this by yourself. If you do all of S estimate, you'll find that beta 1 hat is not equal to 1 over gamma 1 hat. So that means you cannot just fit one model and apply it to another. Why is that? The reason is, for simple linear model, we have this interesting formula for the coefficient. So beta 1, for simple linear model, we know it's equal to the R, which is the same R here, sample Pearson correlation times the standard deviation of, let me just say y1 to yn, divided by the standard deviation of x1 to xn. That's the formula we have for the slope, simple linear model. While for the gamma 1 hat, you will have the slope as also the sample correlation times standard deviation of the new response, that's x1 to xn, divided by the standard deviation of y1 to yn. So you see, they're not reciprocal of each other because R is still R. We do not take its reciprocal. So if you really want to have that symmetry, right? I take the y as x, x as y, I fit a line, and the line will be just symmetric with my original line by having the 45-degree line as the center. If that's the thing you want to have, then you cannot use ordinary least square. Instead, you can use something called the major axis regression. So if you want, let me write down the two lines, let me say y equals beta 0 hat plus beta 1 hat x, and x equals gamma 0 hat plus gamma 1 hat y, be symmetric about y equals x, the 45-degree line. If that's what you want, then you should use the major axis regression, because the ordinary least square estimate does not satisfy this. And what does the major axis regression do? What does it do? So it's actually not trying to minimize the vertical distances or squared vertical square residuals as we do in the ordinary least square. What it tries to minimize is basically the perpendicular distance between every point to the line. So that means you are treating the X and Y symmetrically. While here, we only assume that the errors is vertical error. We do not assume there's horizontal error in our least square. Okay, so that's just something I just talk about as an extension from our linear model. In linear model, least square is still the predominant estimation approach because of the model assumption and because of the maximum likelihood estimation. Okay, so as a follow-up from this regression coefficient or this coefficient determination, we can also talk about partial correlation. So partial correlation is another topic which is very useful in practice. So specifically, in our two predictor case, we can say that we want to get a partial correlation between y and x2 given x1. So in other words, I want to know how much does my response correlate with my predictor 2 given predictor 1. So partial correlation can give you an answer to that. But you may wonder, why do I need this? Why cannot I just use beta 2? Why isn't beta 2 sufficient? Or I should say beta 2 hat sufficient. Let's say you fit a model from using, okay, so here, let me say that I just put it here so it's clear to you. Y hat is beta 0 hat plus beta 1 hat x1 plus 1i plus beta 2 hat x2y. Let's say that I fit this all as I have beta 2 hat already. Why isn't beta 2 hat sufficient? And we said this is the effect size, right? Effect size estimate. Why cannot I just use that? This is capturing the conditional contribution of x2 given x1. The reason why this is not sufficient is because this thing is not scale free. Okay, so the answer is that, so the absolute value of beta 2 hat, because usually we don't care too much about the sign. The sign just means the direction changes, but it's not the magnitude, right? This effect size estimate is not scale free, unlike our correlation coefficient, which means that you can imagine if I just multiply my x2 values by 10, then correspondingly the beta 2 hat will be divided by 10. So it will change with the scale of your measurements. So this is another question many people will encounter in practice. That is, do I need to standardize my predictors before running a linear regression? What's your take on that? Okay, so yeah, does anyone want to say something?
No, not usually. You don't have to, unless you're using certain types of like machine learning techniques. But when you're doing OLS, not usually, no.
So you said usually you do not need to, right? Yeah. So for exactly, so for the prediction purpose, so you do scaling centering or scaling will not change your prediction. So your yi hat will stay the same. And also the residuals will be the same, of course. But what will change will be the beta 2 hat. Those estimate values will be changed, right? Like I said, if you do scaling, they will be scaled as well. So that's why you do not want to really interpret the magnitude as it is because it's changing with scale. So you want something like the partial correlation to be scale free, just as the Pearson correlation for linear relationship. No matter you scale your X or Y, but the Pearson correlation will stay the same. So that's why we want something like that. Okay, we want something scale free, just like the Pearson correlation. That's what we need for the partial correlation. So how do we define the partial correlation exactly? So you can define it as based on two linear regression. Okay, so the first one, computation. The first step is that you regress your response on the predictors you want to be conditional on. So regress y on x1, okay? And then you will get the residuals. I call this residual EY given x1. Second, you regress your x2 on x1. You get the residuals. And you call this EX2 given x1. And finally, you compute the Pearson correlation between the two residuals. Okay, then you compute the sample Pearson correlation between these two residuals, EY given x1 and EX2 given x1. So based on this procedure, you can see that this x1 may not be just one predictor. You could have a set of predictors to be conditional on. Let's say you have p-1 predictors and you are interested in the partial correlation between y and one of the predictors. Then you will be conditioning on the remaining p-2 predictors. Okay, so x2, x1 can be a set of predictors. So geometrically, what does it mean? So you can consider that geometrically, it's just like when you take the residual, it's basically what? It's basically, there's a graph in the notes. I'm going to send it, post it very soon, so you can check it out. So I'm not going to draw it here. So geometrically, you can think of linear regression as a projection. Okay, so this means that you want to project y onto the, so you can think of, sorry, let's say this. So you can think of x1 as an n-dimensional vector and a point in an n-dimensional space. So y is also a point in the n-dimensional space, so is x2. And you know that in the n-dimensional space, every point can also be represented as a vector. So that vector actually go from the origin to that point. That's a vector. So I have three vectors. And so linear regression means that I'm projecting the vector y onto vector x1. And then I take the residual as the difference. So basically, I'm going to draw here. So let's say this is the vector x1. This is the origin. And if my y is this, okay? So what I can do is that after do the projection, I would have y decomposed into two vectors, okay? So this will be the y hat, okay, y hat using x1 to fit only, and this will be my ey given xy. So this is the residual vector. It's another vector in the n-dimensional space. So similarly, I will get a residual vector for x2 given x1. Then the sample Pearson correlation between two vectors in an n-dimensional space is just the cosine of their angle. So let's say that if I have another one, ex2 given x1 as this, then this angle, let's call it theta. Then this thing will be equal to cosine theta. So that's the geometric interpretation of the partial correlation. So how do we interpret it? So let's say that if I have y and x2, if I do not do this partial correlation, It's possible that y seems to be highly correlated with x2 just because both of them are correlated with x1. So that will make them seem very similar to each other. But if I remove the effect of x1 from both y and x2, then I'm interested in seeing, are the two residual vectors still correlated? Because if they do, then that correlation will have nothing to do with x1. So in other words, we remove the effect of x1 by doing this regression. So that's why linear regression is very useful for accounting for so-called confounders in our data analysis. So in this case, you may consider, you may consider x1 as what you call confounder, and whose effect on y is not of your interest. And then y is the response, and x2 is the predictor of interest. So you're very interested in how x2 can affect y, right? So usually you are doing this in the causal inference setting kind of, but you are not giving the causal data. The data is just observational data. So you do not know who caused what. It could be y cause x2 or x2 cause y. But no matter what, the association you are interested in is still just between those two. And you don't want this association to be driven by a confounder. So for example, in genetics, you may think of this response as your phenotype, like your blood sugar level or your BMI. And you can think of this x2, your predictor of interest, as one element in your genome, your genetic element. And the confounder would be the environment. So we want to correct for the environment before saying, okay, is there any association between the genetic element and the phenotype? So that's what people do in practice. Okay, so that's just a partial correlation. You can think of it as an extension of the Pearson correlation by adjusting for confounders. So as statistical inference is our primary interest, right? So how do we test whether a correlation is zero? And this applies to both the Pearson correlation and the partial correlation. Okay, so how do we test? How to test whether correlation is zero? Whether two variables have zero correlation in population. So this is something we mean by statistical inference. You want to infer a population quantity. So for this example, let me just give you the definition of population correlation and sample correlation. So for population correlation, it's determined by the joint distribution of two variables, x and y. So let's call this rho between these two variables, x and y. So it's defined as the covariance of the two variables. And by the way, the two variables are both scalar variables, one-dimensional, divided by the square root of variance x and variance y. So clearly you can see that this definition is only concerning the distribution. It's not about our data or a particular sample. So correspondingly, let's say we have sample correlation. Then this will be based on realizations of the two variables. So let's call them x1 to xn, the realizations, and y1 to yn. We have n observations for each variable. Then the sample correlation, we call it xr, r for the sample, rho for the population. So this one can be computed just based on the sample. So to put it simply, so it's just xi minus x bar times yi minus y bar, and the summation is over I from 1 to n. And in the square root denominator, we have the summation xi minus x bar squared times yi minus y bar squared, I from 1 to n. That's it. So then our statistical inference is concerning the population correlation. So we want to test whether rho xy is 0. And our test statistic is the sample correlation. So then what's left is the distribution of the sample correlation when when this null hypothesis holds, right? When the rho xy is 0. So Fisher has something called Z transformation to address this issue. So basically, the Z transformation is based on the sample correlation by transforming it. So that means here, I'll just write it down. Fisher's Z transformation. It's a very small transformation that gives us a normal distribution. So it defines the Z statistic as just 1/2 log of 1 plus R xy over 1 minus R xy. So this is the Z statistic. And Fisher basically showed that, and he showed an asymptotic distribution for this. So the asymptotic distribution is that we would have root n minus 3 times z minus 1 over 2. The same transformation applied to rho. 1 plus rho xy over 1 minus rho xy. This will have asymptotic convergence in distribution to standard normal. So this important result provides a way for doing hypothesis testing, because you can see when rho xy is 0, you will have 1 plus 0 over 1 minus 0, that's 1. Log 1 is 0, so this term goes away. Then you can see that under the null, you would have z being approximately just normal distribution with mean 0, and the variance is approximately 1 over n minus 3. That's by dividing this term into the variance. So this allows you to do a very simple, quick test for correlation being 0 or not. And so this is something very useful to know, especially if you want to test whether the two variables are associated. And this is just for the marginal correlation. And we can have similar results for the partial correlation. Okay, so that's all for today. So basically we finished the linear model part when predictors are all numerical, or I can say that we think that numerical measurements are the unit we're interested in. So in our next lecture, we're going to talk about categorical variables, where some of the predictors are categorical instead of numerical. So how do we deal with that? So that's all for today. And so starting from our next lecture, I will try to post the lecture notes before the lecture. So for those of you, at least one day before the lecture. So for those of you who are interested in doing preview of the lecture notes, you can do that. Okay, so see you next time on Thursday.